So my name is Piero Ferrante. I'm the Director of Data Science at C2FO. And today we'll be talking about how you can engineer a contemporary risk management system using Python. Really, I want this talk at the end of the day to just be thought-provoking. The approaches that I'm using here are pretty general purpose. So, it's really just about tackling projects or problems from an objective standpoint. So with that, we can go ahead and get right into it. Before I talk about the lending platform and the underwriting platform that we built, I have to give you a little background about C2FO, the company that I work for. So C2FO stands for Collaborative Cash Flow Optimization. Good luck saying that 10 times fast. But basically, we are the world's first market for working capital. So those are a bunch of words. What does that really mean? I like to tell this example where you have a company like Costco or Amazon, and they have hundreds of thousands of suppliers in their supply chain, right? So if I'm one of those suppliers, say I sold Amazon $10 million worth of t-shirts, typically you'd have to wait 30, 60, or 90 days to get paid from that buyer. But what if you wanted to get paid tomorrow because you need to hire additional staff or start a new factory or something like that? Historically, you would have to go to a bank or what's known as a factorer, and you would take an enormous discount on the nose. But what if that same day your buyer, Amazon, is sitting on 15 billion cash, and they're simply looking to make a 6% rate of return? So long as the supplier is willing to forego that 6% APR, we can match the two up in the marketplace, and what happens is this really synergistic win-win scenario where the buyer is achieving their desired rate of return and the supplier gets the lowest cost of capital available to them anywhere. And we kind of do this at scale. On a given day, we might have a few billion flowing through our markets. We get invoices on a nightly basis from all of these, Fortune 100 type buyers internationally. So think about the velocity of and the volume of that data. And what's really cool is that this problem with waiting to get paid happens to be a very big one. Globally, there's about $40 trillion locked up in just this accounts receivable process. So if you think about the suppliers having access to those funds today instead of 90 days from now, and then you start thinking about the trickle-down effects that can have on the global economy, it's pretty profound. So what I'll be talking about today is WFC, which stands for Water for Commerce. It's basically a small to mid-sized business lending platform that we engineered to complement the C2FO proper markets. So what is it? It's an investment fund from the investor's perspective, where instead of us relying on the buyers to supply that capital, it might be an investor, maybe a mutual fund, maybe a hedge fund, maybe a wealthy individual who's looking for a very particular type of risk-return profile. And these are very short-term loans. So think like 40 or 60 days. So can anybody tell me where else you can find a 6.25% return with a 40-day horizon? Yeah, it doesn't really exist out there. So it's a really attractive investment opportunity for the investors as well. So if that was clear as mud, I drew this picture where basically you see, like if we call B1 a buyer like Amazon, they have all those suppliers in their supply chain. And C2FO proper can service the supplier so long as that buyer is on the C2FO platform. But likely that supplier is doing business with other big buyers like a Target or a Home Depot or something that may not be on the C2FO platform. So that's where WFC comes in. Because at the end of the day, we're the champion of the supplier. We want to get them access to liquidity however we can, whenever we can. So that's where the fund comes in. All right, you guys have probably heard about the lending clubs, the on-deck capitals, the small to mid-sized business lenders are kind of a dime a dozen these days. So why would we want to get into this really crowded, really competitive space? Well, we think we kind of have a competitive advantage with the data that we have access to. Because we're landing these invoices on a nightly basis, and we have been doing so for the better part of 5 years, we have daily information that's highly reflective of that supplier's cash flow situation. So we're in a place that we can underwrite competitively where a conventional bank might not be able to. There's also an aspect of fairness here. So you might have heard some stories lately about some of those other companies in the same space rate gouging the borrowers, where you might be looking at between 20 and 30% kind of situation, which that's rough. You don't want to put a supplier into the ground because they really need that liquidity right then. You can, and some other people will, but that's not really what the WFC fund is all about. And again, all of this is possible because we have good data and we have great tools. So this probably looks like the sticker table if you've ever been to a PyData conference. So we use things like pandas, SciPy, stats models, scikit-learn, Anaconda for managing our environments, matplotlib for plotting stuff, Luigi for orchestrating our directed acyclic graphs of tasks, NumPy, Spacey for NLP, bunch of different technologies, and I'll kind of talk through how each one of them ties to a particular component of risk along the way. So if we think about this continuum of risk. On the bottom, we have these kind of encompassing tasks that we need to do. We need to prospect. We need to understand who's the right candidate for a loan. Then we need to underwrite them. And then once they're underwritten, we need to onboard them, get them into the fund essentially, and get hooks into their bank account so that we can get paid back. And we also need to kind of seamlessly manage this portfolio so that we're not exposing ourselves to undue risk along the way. So, for example, if if inflation goes up and discretionary spending goes down, and we have an undue exposure to the retail industry, right? When discretionary spending goes down, the retail industry is probably one of the first ones to take a hit. So you don't want to be too exposed in that area. But the first thing we'll talk about is this notion of concentration risk. So if we think about the cash flow or the accounts receivable coming in for these different suppliers, all other things being equal, you would prefer that a supplier has multiple sources of accounts receivable, right? Because if you're just doing business with Costco and they say, well, I don't want your product on my shelf anymore, well, there goes a big chunk of their business, or at least the part of their business that would allow them or allow us to underwrite them better than the next guy and get them a lower rate. So we look for things like diversity, and for anybody who's used pandas, so essentially, we have a time series index here, and think about multiple columns having different sums associated with a particular date time for that supplier. With a single line in pandas, you can get a nice looking area plot like that, and you can get a pretty good picture of how diverse a supplier is at a given point in time. We also have this notion of junk. If anybody's familiar with bond ratings or something like that, if a supplier is going to get paid from a Payless shoes 10 days from now, that's a lot different than, let's say, a Costco or an Amazon, because Payless, they're maybe in a difficult financial situation right now. They, maybe they'll go on to do business for another year, maybe 10 years, maybe indefinitely, I don't know. But they're not, at least as far as the street is concerned, the likelihood that they may default and not pay their bills or something like that is a little bit higher than a Costco. So we can factor in this notion of junk and kind of penalize a little bit if the buyers that are going to be paying that supplier are less creditworthy. So that kind of addresses concentration risk. Most of the talk will be focusing on default risk. That's really the most interesting part. So when we talk about architecting this system in Python, that's great, but there are some things that you might want to do in another language like R. So for example, R has a lot of really mature forecasting packages. that have been battle tested for the better part of a decade. That's not to say that you can't port some of these libraries over to Python, because over the past couple years that process has been well underway. But at the same time, if you're looking for a certain level of stability with certain libraries, you might have to rely on another language like R. So how do you make Python talk to R and R talk to Python? Well, there's this great thing called RPy2, where basically you can take like a pandas data frame and then convert that into an R data frame or an R time series, and then you can do your parallel tasks or call your parallel functions in R, get your results set back, and then move them right back over to Python, and you're working all within one nice clean code base. You're just setting, you're just embedding that string of R code right there in your Python code, and it knows how to do everything else. So for invoking models like autoregressive integrated moving averages, and when we want to do things like Holt-Winters exponential smoothing, and there's also this really great Bayesian structural time series package that the folks at Twitter released not too long ago, which we use in R as well. Think about using RPy2 if you have things that you need to do that aren't available in Python yet. The good news is that libraries like PyFlux are starting to include some of these models, so that hopefully I can move all of the code base back to Python in the very near future. So what does this look like when we're forecasting a supplier's AR? You see in the plot on your left, we make a prediction, that's the red over there, about 90 days out, a quarter. And you can see the plot on your right, even though it's a little bit cut off here, or very cut off rather. Basically, it shows, historically, if we were to make that 90-day forecast without observing those last 90 days, how far off would we have been? Were we within 1% margin of error? Were we 100% off? And we apply all of these different modeling techniques for each supplier every night. So I mentioned before, an ARIMA model, a Holt-Winters model, a Bayesian structural time series, and OLS regression. Think about those four models, and then think about the hyperparameter space associated with each one, and then think about doing that for about 250,000 suppliers every single night. That problem gets very big very fast, but we need to constantly be in the best position to forecast out the next 90 days for that supplier so that we can underwrite them. And typically we look for about 1.25 years of history so that we can observe an entire year's worth of seasonality. This supplier here, you can see that they have a very distinctive pattern, kind of like a metronome, super predictable, and that's what we generally like to see, nice tight prediction intervals. And when we're evaluating these models, we look at things like the mean absolute percentage error, the MAPE, and the root mean squared error. And we kind of have our own little algo that we rolled that combines the two and weights the two so that we're choosing the best forecast on a nightly basis for all these suppliers. And somebody earlier today talked about all of the different plotting options in the Python ecosystem. There are a lot. You have Plotly, you have Matplotlib, you have Pandas plotting, which is really just kind of like an abstraction on the Matplotlib API. And there are lots of other ones. But what I really love about good old Matplotlib is if you're just looking for a static image and you really need to do some extensive stuff, you can. You really, there's not much limit to the level of extensibility of a Matplotlib plot, which is great. You see over here in this bottom right-hand corner, there's a probability that we plotted. I'll be talking about that a little bit later. Subplot underneath. So you can do quite a bit. So the next thing I want to talk about as it relates to default risk is this notion of seasonality. So in stats models, you can run what's called a seasonal decomposition pretty easily. So what the seasonal decomposition seeks to do is take a signal, and then it wants to decouple the trend aspect of that signal from the seasonal aspect. And then whatever it can't explain between the trend and the seasonality component is the residual, what's left over, what's inexplicable. But it's very easy to run a seasonal decomposition. Typically, you look for a smaller residual. That means that most of that signal can be explained by trend and season. But you get out these nice plots with just a couple lines of code. So keep at it, stats models. The next thing I want to talk about is this notion of AR discontinuation. So let's contrast this from bankruptcy. Bankruptcy is a complete nuclear event, right? A business says, I can no longer fulfill my debt obligations. But AR discontinuation, at least the way I'm defining it, simply means the likelihood that all of the buyers that they're currently doing business with that are on the C2FO platform stop invoicing with them. They say, I don't want your product anymore, whatever it is, okay? And you can understand why that would be very interesting from an underwriting perspective, right? Because without us seeing that daily cash flow from those buyers, that's our ability to underwrite for that supplier. So when you're framing a problem like this, as a machine learning problem, you need to pay attention to things like data leakage. Has anybody heard that term before, data leakage? Two of you maybe, okay. So basically it boils down to do not observe that which would not have been observable at the time you would like to make the prediction. So if we want to get a 45 or 90-day jump on, on a buyer discontinuing invoicing with a supplier, when I'm training my model, okay, I can know that buyer stopped invoicing because that supplier would have eventually flatlined, but the data that I'll use to train that model would have to be 45 or 90 days in advance of that flatline, right? Because otherwise you're cheating, right? So be cognizant of data leakage at all times when thinking about problems like this. Once you've kind of framed the problem, then you need to engineer some interesting features. So features is basically just machine learning speak for variables or attributes that you're going to dump into your model that are hopefully going to help explain what you're trying to predict. So what I like to do, just a little feature engineering trick when you're dealing with time series data, you can think about engineering features like averages or month-to-month differences or quarter-to-quarter differences over the entire span, all of history. You can take like maybe a 13-week or some kind of smaller window and engineer features off of that, and then you can take like just the very last observation that you would have had within that time window and engineer features off of that too. And applying some windowing techniques to your feature engineering, at least from our experience, has yielded some very interesting results. So what are we using to do this stuff? So as far as feature engineering is concerned, scikit-learn makes things like encoding categoricals or making dummy variables a breeze. If there are any physicists in the room, when I say a polynomial feature, I really just mean like an interaction variable where you're multiplying one thing by another thing. We also need to scale some features depending on the type of classifier that we're training, or maybe we need to achieve some type of unit variance. And sometimes you might need to do dimensionality reduction, or to keep your model fairly simple, you might do some feature selection or elimination. Because what's the point of including 15,000 different variables if you can get very comparable performance with just 87, right? You don't need that added complexity. And a lot of times what we've seen, we have all these different competing models that run on a nightly basis to predict these types of things, but I'll tell you, spoiler alert, XGBoost, if anybody's familiar with that library, crushes often. So if any of you are Kagglers out there, who's familiar with Kaggle? Okay, so kind of machine learning competitions that big companies put out there for developers or aspiring data scientists to kind of solve in a collaborative way, and then there's a ranking process. Long story short, XGBoost crushes. And it's an implementation of gradient boosted trees, so they're very, very performant, a little expensive to run sometimes. And we use XGBoost in conjunction with the hyperopt library to grid search our hyperparameters. So there are all these different parameters that you can turn the dial this way, pull the lever down, change all these things around, but you want to search an entire feature or an entire hyperparameter space to ensure that your classifier is performing as well as it possibly can at a given point in time. Long story short, our models are performing pretty well. So what you're looking at here is a plot of the recall, or the number of suppliers that actually ended up discontinuing invoicing that we would have predicted, the true positives that we got right over time. And you can see, generally speaking, it's been improving. And that big spike was something horrible went wrong that day. It was probably a very long night for me. Some of the models broke. I don't want to gloss over this last point here. Do not overfit. You guys always hear about overfitting when it applies to machine learning, and with a classifier like a gradient boosted tree, it's really easy to overfit if you don't know what you're doing. So pay attention to the details in that regard. I talked about predicting AR discontinuation, but let's talk about bankruptcy for a second. So I need to know that the likelihood that this supplier, who might be an industrial manufacturer located in Atlanta, Georgia, and they've been an LLC for 15 years, and they have approximately this many employees, I need to know the likelihood that they're going to have that nuclear event and just go bankrupt. So what you first need to do in order to predict something like that is learn what the outcomes were. Where did the actual bankruptcies take place? So Shocker, the national database for kind of collecting all this bankruptcy information, which is known as PACERS, is really excruciatingly difficult to use. Not a good API, get slapped on the wrist for scraping and those kind of things. So we needed to get this data in a clean format so that we could train these models. So let's see. Once we get the data, though it's not necessarily that easy, because what the bankruptcy database might call a business and what we have on file for that business might be a little bit different. So Joe's Plumbing LLC, that's what we might have on file, but then the bankruptcy database might have Joe's Plumbing of Greater Kansas City LLC or something like that. So we need to go through this matching process. So has anybody here done any kind of string matching or anything like that? It's a pretty tedious process, a lot of different techniques that you can use to do string matching. But before I get to that, I want to do the easy stuff first, right? If I have some metadata that says this is this supplier's tax ID or this supplier's phone number, I want to reduce the size of my search space so I don't have to string match absolutely everything, because I have better uniquely identifying information. So I'll look for stuff like that first. Tax IDs and phone numbers. Then we can start doing some of the string matching. And an interesting trick that I found, because it was very, very expensive to compute the Levenstein distance, the Yarrow-Winkler distance, Jacquard distance for all of these suppliers on a nightly basis, you can take a SoundX. So a SoundX is basically a codified representation of the way it sounds to say something, and you can then eliminate the search. You can then refine your search space a little bit more, so you don't have to do, you don't have to do the those distance calculations for every single supplier. You're just calculating those distance measures on the ones that sound like the one that you're looking for based on the SoundX. So that's a neat little trick. And then because I have addresses on both sides in the bankruptcy data and in the C2FO database, then we can simply calculate the Haversine distance between the two locations. So think about if I'm within the ballpark, if I'm within like a 5-mile radius or something like that, perhaps that has a multiplicative effect on the algorithm that I designed to weight those different distance measures. And then you kind of tinker with it, and you get it to a point that you feel comfortable and that it's yielding the right kind of results. When you're doing something like this, just my little pro tip, if you are rolling your own, I would look at the libraries that are implemented beforehand. But if you're really content on rolling your own, think about Pythonizing that code so that you stand to benefit from the static compilation, because things like Haversine distance in pure Python are going to be really, really slow versus a Pythonized version of that same code. Or you might look at, if you're just doing some matrix operations, you may look at a library like numba, where you can just write a function that contains pure numpy, decorate it with a little just-in-time decorator, and you stand to benefit from a massive speed up by doing that too. Just a couple examples. You see like a Snuggle Pet Products LLC versus Snuggle Pet Products. The F ratio was very high, the F partial ratio was very high, the Jarl Winkler was very high, the Jacquard was very high, and the geodistance was approximately 25.7 miles. So likely we had the proprietor's home address on file somewhere and then their business address. So that gave us additional confidence that this was in fact the same entity. When you look at that bankruptcy data on a national level, and again, this is data from the States, some of the kind of conventional wisdom bubbles up. You always hear that running things like hotels and restaurants are kind of notoriously hard businesses to keep up and running. So you can see over time the bankruptcies. Right after the financial crisis in 2008, there were quite a few. Generally speaking, it's been trending down. But things like repair services, legal services, hotels and motels, restaurants and eateries, those are some of the biggest offenders when we're talking about bankruptcy. Not the most inspiring factoid for an aspiring entrepreneur here, but this heat map here is telling us that on the x-axis you have the employee count, and on the y-axis you have the company sales. So generally speaking, the less sales you have and the fewer employees that you have, the greater the likelihood of bankruptcy. You do see some of the bigger boys down here filing as well, but not nearly as frequently as the smaller companies in the upper left-hand corner. So good, great. We can train all these great models for bankruptcy and AR discontinuation, and we know how diverse a business is based on their invoicing pattern with different buyers. But now, how do you know if somebody is just a bad egg? How do you identify those bad actors that are lying to you when they're inputting their data during our onboarding process? So we have supplier relationship managers that will actually call a supplier and have a conversation with them about how to onboard for the fund, and we're listening to that conversation. We're diarizing that conversation. We're saying, okay, the person from C2FO or WFC said this, and this is the supplier saying that. So taking that audio recording and identifying the speakers in it, and then we're going through all the words that the borrower or potential borrower is saying. We're looking for things like debt, leverage, bankruptcy, lien, payroll, layoff, credit, Cayman Islands, red flags in terms of a company that may be doing something a little seedy that you don't want to be involved with. So this is just an example of what one of the transcriptions looks like over on the right, and I highlighted the area that was particularly concerning within the context of this call. Realistically, you couldn't pay somebody enough to sit there and read these things all day and highlight stuff. So we need to use libraries like Spacey that can lemonize and then tokenize all of this text and make the computer do that pretty trivial work, which is just looking for these specific terms in their kind of root form. And Spacey, I can't say enough great things about that library. Very thoughtfully written. And it's very, very fast. So another way, and sorry for the math on here, another way that we can kind of determine whether or not a supplier is being forthright and honest with us is we have the invoices from the buyer too. So if we say, hey, you want to borrow from us at 7%, great. We need you to upload all of your invoices. And then what we can see is if those invoices are true, because we have the source of truth coming from the buyer, and we look for if the count of invoices matches up, if the amount across all these different invoices match up. And we call it this invoice congruency score, but that's pretty much the gist of it. And that tells us, hey, are they falsifying some of these invoices? Because again, we do have access to the source of truth from the buyer. So talking a little bit about fraud, weeding out all of the bad eggs. Then if they pass the underwriting process and they're not a fraudulent supplier, then they might make it into the portfolio, okay? And then we need to start thinking about, what separates a good supplier or a good borrower from a bad borrower? All of those different models and scores that I mentioned earlier, they kind of wrap up to what we call the WFC score. It's kind of our opinion about that borrower. Just like you have a FICO score, a credit score in the US, this is our opinion about a given borrower. I mentioned, though, that to do a forecast, which is a big component of the score, you need to have observed at least 1.25 years of history. Now, that doesn't encompass all of our prospects. So a little machine learning trick, right? We want a score for those individuals, but they're missing this one piece. So we can train a model, actually, on all of the other suppliers or all of the other potential borrowers, and then we can impute what their score would have been without having that component. And that gives us total coverage across the entire prospect pool, which is what we're looking for, because we want to rank order the best prospects and the worst prospects. All right, so now they have a good score. They didn't mention, alcohol problems or Cayman bank accounts over the course of that phone call. They've uploaded all their invoices. They look great. Okay, what's next? So we need to figure out how much are we going to lend to them and over what type of duration. So it's pretty simple. If my forecasts are any good and I know how much they're going to be getting paid from these buyers over the next 90 days, and they have a very high WFC score, then I'm willing to lend them a greater amount, right? So if they have a very low WFC score, then I'm only willing to give them a very small amount. Looks like I'm woefully at the end here, so I need to fast forward just a little bit. We monitor a lot of different things over the course of that supplier's lifetime. We monitor all the aspects that go into the WFC score, and we use Luigi to generate a directed acyclic graph to handle all of the task execution, and we use Anaconda to keep to manage our environment and keep things pretty simple. So I can't say enough good things about those two libraries. That DAG, I thought it actually looked like a Cobra for some reason, so I might rename it Project Cobra. Not sure. All hail Project Cobra. All right. So I was initially going to show a demo, but we are going way over time here. Long story short, I used a library called Spyre, which is a port of our Shiny that allows us to create a lightweight web application that uses Cherry Pie and Jinja 2 for templating. Really easy to use, and this is what it looks like. So what? Objectivity gives way to innovation. Better independent data beats more complex algorithms. You always have to consider different trade-offs when you're engineering a complex system. And last but not least, creating great solutions with open source software is part of open source too. So, people that are contributing to open source, that's great, that's fantastic, but we need people building great solutions on top of those libraries at the end of the day to keep the trajectory and the momentum going. So with that, thank you very much. I'm sorry for going over.